Hi, my name is Zoran. In this video, I will show you how you can entail a formal mathematical proof of correctness of a complex, large function. If you like what you see in this video, you can follow me on Pluralsight and watch my video courses there. There are 60 hours of video courses I have published so far at Pluralsight. This video is the second in a mini-series. In the first video, we have implemented a function and applied the incremental coding technique, which helps us develop a complex feature without, or at least with minimum possibility of adding bugs to it. Take the links from the description of this video to watch the rest of this mini-series. So after covering incremental coding, today we will talk about proving correctness of code, and after that, in the next video, you will learn how you can add pieces of code that are demonstrating that the code is correct as it runs. And then in the fourth episode in this mini-series, you will learn how to write code so that code itself reads as the proof of its own correctness. That will be magic, but before we get to that magic, there's a lot to learn. One step you must understand, you must keep at the back of your mind all the time when you're developing code, is that code correctness can be proven. Please subscribe to my channel. Don't forget to tick the bell so that you receive notifications about new videos in this series and in other parts of my channel. Now let's step to entailing the proof of correctness of a piece of code. In the previous demonstration, we have developed a function which implements the Quicksort algorithm. Here it is. It used to work correctly. It appears to work correctly, to be very specific. There is this testing function which demonstrates on different sizes of the list that the sorting function is really sorting the data. It is a recursive implementation. This is the termination condition. When the list has no more than one element, it is already sorted. Then there is a portion which selects the pivot element. Then comes the partitioning step. And when the gap is entirely consumed, the partitioning is over. And we can recursively sort the left-hand partition and the right-hand partition. If you have any second thoughts about how Quicksort works and how this function was implemented, please watch the previous video on incremental coding. That is how we made this function be. The topic of this video is how do we prove that this function is correct? How do we know that it does sort and it has no bugs? To do that, we will define predicates that must evaluate to true. One kind of predicates is called post-condition. That is the predicate that is true after the function completes. So we could say, after this function completes, the data is sorted. Well, yes, of course, but that's not mathematical expression. We are not discussing philosophy of coding. We want mathematical form of it. So here, this is one possible definition of a sorted list, so that for any distinct indices inside the list, the item on the left is less or equal than the item to the right of it. We could write it differently, like for any index greater than 0 that belongs to the list, the item just to the left of it is smaller or equal than that item. If you want to practice, take this second definition of sorting and try to entail your own proof of correctness of this function using that criterion. I will stick to the first one, but there is one more criterion, one more predicate that must always be true for any function. The function must terminate. The function that doesn't terminate is not a programmatic function. It's not correct. So we must prove two attributes of this function. When it ends, first it ends sometime, and after it ends, the data are sorted. This quicksort of list is just delegating to the quicksort of span. So if quicksort of span satisfied the same set of post conditions, then this quicksort of list will also satisfy them. So we are moving to the second function and we can ignore the first one. When the length is not greater than 1, when it is 0 or 1, we can check that both post conditions are satisfied, so everything is alright. Why is this important? It's important because after this return statement, if it didn't execute, we know precisely that length of the span is strictly greater than 1. It is very important. So the proof of correctness boils down to entailing everything you can entail about the system. We know that span length is greater than 1 here. Alright. And we use that to calculate things about, for example, this middle point, which will be used in selecting a pivot. We know that it is greater or equal to 1, and we know we can prove that it is strictly smaller than length. Now we know that middle is greater than 0 and strictly smaller than length, and we know that we are safe to use it as an index inside the span without causing index out of range exception. So middle is a valid index inside the span, proven. These 4 lines are using it as the index and they will not crash. After these 4 lines have executed, we know that there will be an item at index 0 and we will call it the pivot. We also know that upper is at least 2, and we know that this loop will run at least once, because it will be strictly greater than the lower inclusive variable. So we get to the loop. We must prove certain attributes of this loop that will help us entail the proof that the span will be sorted after the function terminates. Look at this inner while loop. It is moving the lower inclusive variable to the right, and it is checking all elements, comparing them to the pivot. So after this inner while loop terminates, we know that for any index smaller than the lower inclusive variable, the partitioning attribute that all elements on the left in the left partition are smaller or equal to the span of 0, which is pivot, that partitioning attribute will be true after this inner while loop terminates. We also know that the lower might reach the upper at the time when the while loop terminates, and then we go to the second inner while loop, which is moving the upper exclusive leftwards. If nothing happened, the upper will remain equal to span length and there will be nothing to check. If upper exclusive was reduced, then we can prove that everything to the right of it is satisfying the right partition attribute, that it is strictly greater than the pivot. And now we hit the if. If upper is still greater than the lower, then there is a gap. There is a gap, alright? So we need to do something with that gap. But inside the if, we know that the lower is less, strictly less, not less or equal, but strictly less than upper. And we know something else. If you observe these 2 while loops above, if the gap between lower and upper was just 1 element, then that element would be consumed by one or the other while loop above. So we know that it is not just 1 element, but at least 2. Do you see how this proving goes? It is a very delicate process. It is like a detective work. You are taking all the information that comes and using it to entail more and more information that is true. We conclude that the gap is at least 2 elements wide. Why that is important? Because we are moving both the upper exclusive to the left and lower inclusive to the right. And we can move both of them because there is at least 2 items in the gap. You see? And because gap was at least 2 and we moved indices by 2, after this if, lower bound will be less or equal to upper, but never greater. We know that it will never be greater than upper. There's more. What is this if body doing? We know from termination of the first while loop above that lower is index contains an element greater than the pivot. We know that the rightmost element is containing a value that is less or equal to the pivot, so we have an inversion. Those two elements must be swapped to restore the attribute of partitioning the left and right hand side. That is what this swap operation is doing. And we have a proof that after swapping, the partitioning order will be restored in both partitions. It's a very nice piece of proof. And now we know that after the if instruction executes, both left and right partitions will be correct. And we know more. We know that after if, the lower inclusive index will be less or equal to upper exclusive. If it is a lower, the outer while loop will continue, but if it turns out to be equal, the outer while will terminate. So again, we have the termination condition. And when the loop terminates, we move to the final stage of this function by swapping the pivot into the middle position. Now we know that span of middle will be the pivot, will be equal to pivot, so we can entail that everything to the left will be smaller or equal to the span of middle, and everything to the right will be strictly greater than it. And this is where we come to including mathematical induction into the proof. So mathematical induction is a proving method which is recursive in its nature, just like this function is. It starts from the trivial case, so you need to have a root case which is satisfied. Span, which has size 0 or 1, is sorted, so we know that the span of size 0 or 1 satisfies the claim that this function is sorting them. And then mathematical induction says, if you know that there is a case, a trivial case of a small size, and you can assume that for a problem of size n, for all sizes smaller than n, the predicate is satisfied, and you can translate the problem of size n to sub-problems of smaller sizes, then you have the complete proof that the predicate is satisfied for all values up to and including n. The span is sorted when its size is 0 or 1, and that is trivially correct, so we concluded the proof completed. And we assume that this function will sort every span that is smaller, strictly smaller than this one, then by delegating sorting of this span to sorting of smaller spans, will make them sorted as well, and by transitivity make this large span sorted as well. This is how the proof goes. We can assume that the sorting of a smaller span will succeed and make it sorted, and we can also prove that this will terminate, because if you observe closely, the range of the smaller span will be smaller than the range of this span. The size will shrink, not become smaller or equal to this size, because if it is smaller or equal, then there will be a corner case when it is equal. And then the recursion will repeat on the same size of the span and it will never terminate. So we don't have a termination condition proof. This is the proof that every next span in a recursive call will be strictly smaller, and so eventually it will shrink to 0 or 1 and just terminate without making further recursive calls. The right-hand side will also sort itself by recursive call, and now we can combine these two. If the recursive call on the left has sorted the left partition and the middle point is standing right in the middle of these two, and the right-hand side was sorted by the right recursive call, then the entire span will be sorted. We can prove that this predicate is true, so the span will be sorted. Termination is also important for the right-hand side. We can also prove that the range of the right-hand partition is strictly smaller than the range of this span, so both partitions will be smaller, each of those will be smaller than this span, and the recursive calls will terminate. We have just proven, quite formally, there is nothing missing in this proof, that after calling this quicksort function, the span will be sorted and the function will terminate in a finite time. That is what was supposed to be demonstrated, and the proof is complete. Okay, this completes the demonstration how you can entail a proof that a piece of code is correct. You may think, hey, this is crazy, who's gonna do this to code? Think of a sensitive financial algorithm as an example. Can you prove that a function that moves money around guarantees that the balance will be zero or there will be a money leak? That is the sort of software where you do prove correctness of code. But in most cases you will not be so inclined to entail such complex proofs to every single function. What I want to say is that you should know that this technique exists, but you don't have to implement it or apply it every single time. That is why in the next video we will demonstrate runtime proofs, runtime predicate evaluations that are demonstrating that all the parts of the function are working correctly or as expected, so that the function is entailing the demonstrative proof of its own correctness as it executes. Now, that will be crazy, but it will be simpler than this one. So again, follow the links from the description of this video. That is where the link to previous and the next videos in this mini-series will appear. And see you in the next demonstration, where we will change all this code in this function so that we don't really need to write all these predicates and proofs and parts of the proof that I wrote in comments. There will be an executable code that does that for us. Thank you for watching and see you later.